Okay, so this, I just wanted to go over one of the test 3s right here. And so hopefully this is the one you had right here. So here on this first one, I just have two masses coming in, colliding, sticking together, and then they move out this way, right here. And so first of all, I ask you to write out the momentum equations. Well, in the x direction, this one has no x component, so all you have is the x component of that one. If that's VB, this component is VB cosine 60 times 6m. So there's the total momentum before, and afterwards it's 7m VC. So there's the x component. The y component, we got mv minus 6m VB sine 60 equals 0, because it's all going horizontally afterwards. So then I ask, what is VB and what is VC? So first of all, from this equation, we can get VB. We do not want to keep any sine 60s in the answer. Sine of 60 is the square root of 3 over 2. The m's drop out. And so we can solve for VB. That's just 3. VB is, bring down the 3 and the square root of 3. So there is VB right there. Then now we can take this VB and plug it up into there and get VC. Divide out the m's, so you just get 6/7. Cosine 60 is 1/2 times VB, which is this right here, and that equals VC. Well, the 3's all drop out, and this is V over 7 square root of 3. Okay, and then I said, what fraction of the original energy was lost? Well, first we'll find the original energy. Well, it's the kinetic of this one plus the kinetic of that one. 1/2 mv squared plus 1/2 6m times vb squared. Well, that squared is just 27 right there. And so this, I'll pull out the 1/2 mv squared, and you're just left with 1 plus 6/27. And then I can combine the 1 plus 6/27 to 33/27. Okay, so there's the original energy. The final energy is just the energy of that one, which is 1/2 7m times that squared, which is v squared over 49 times 3. Well, we can get rid of a 7 and a 49, which just gives me a 7 times 3 is 21. So I'll pull out the 1/2 mv squared, and we just got 1 over 21. Then if we wanted to get the energy loss, it would be whatever you had at the beginning minus whatever you had at the end. So just subtract the 2 right there. Getting a common denominator, which was 63, 74 over 63. And then if I wanted to get the fractional loss, you take this number and you divide it by that one. Take this, divide it by that, the 1/2 mv squares drop out. And you just get 74 over 63 divided by 33 over 27, which just simplifies to 74 over 77 right here. So there's that first one right there. Number 2, right here, if we go to the second one. Here we had a disk, and we had a block of mass 3m that had a mass of m. And this one's on an inclined plane, no friction, it was smooth. Right here, 30 degrees here, and what did I say? I said, write out the energy equation from first released to the bottom, and that distance was 10r, right here. Well, if you look at the energy equation, the only thing you have is potential energy. This one isn't going up or down, so all you have is 3mg times that height, and that height is 10r sine theta. So there's the potential. Then when this gets to the bottom, it has kinetic, 3/2, because it's 3m v squared, plus this thing's turning, 1/2 I omega squared. And since the rope isn't slipping, it's v squared over r squared. So there's your energy equation. I also said write out the force equations on this and the torque on that. The force equations on this block, you got 3mg sine 30, minus t equals 3ma. We could have written out the force in the y. We don't need it, but you have n minus 3mg cos 30 equals 0. And then we can write out the torque equation. The only torque one we have to worry about is the tension. It's just RT equals I, 1/2 mr squared alpha, which is A over R. Again, the R's drop out. And then I ask, what is the tension? Well, we use these two equations. So I'll cancel all the R's cancel. So this bottom one is just T equals 1/2 MA. The top one is 3/2 mg minus T equals 3 MA. If we just add these two equations together, the T's drop out, you get 3/2 mg equals 7/2 MA, or A equals 3/7 G, right here. Now we can take that and put it right up into here, and we got the T, it's 3/14 mg. So there's the tension right here. Now I said the time for this thing to get down. Well, from this equation right here, we could just use the A right there, but well, I guess we will use that A right there, but we'll come back to here. This is 30 times 1/2, so it's 15. The M's dropped out, 15 GR. And over here, the R's drop out, and you get 3/2 plus 1/4, which is 7/4 V squared. Okay, so we could solve for V right here. I don't even know if we needed it. I didn't ask for it, but if I did ask for it, it'd be 60 over 7 GR square roots. But we don't need it because if we wanted to get the time, we'll just use this equation right here. X, which is 10R, 0, 0, started from rest, 1/2 A, which we have as 3/7 G, times the time squared. So there's that equation right there. Solve for the time. So it's the square root of 140R over 3G. And then the last thing I said, what is the total work from top to bottom? Well, the only one that's doing any work, it's certainly not the normal, and it's not the ropes. The only one that's doing any work is the gravitational. How much does gravity give off going down? Well, it just gave off the what? All this potential, which is 15 mgrs. So there was the total work right there. So you could have got it by the change in kinetic, but we already know the change in kinetic was the final minus the initial, which is 0, which is just this right there. So, okay, so there's the third one. Third one, it says 3-point masses, M, 2M, and 4M are in a line in deep space. That just means you don't have to worry about gravity or anything. These two are just sitting there, and this one's moving at a velocity v. And it's going to collide with this one right here. With all the collisions are head-on and elastic. So first, this one's going to collide with this one. And since you're running into something bigger than you, you're probably going to bounce back, and then that one's going to take off right there. So we can look at momentum on this collision. The momentum before was just mv. Afterwards, this one was 2mv2 minus, since it's coming back, mv1. We can use the relative speed equation. The relative speed of approach is v. V is v right there. The relative speed of departure, they're both just deviating right there, and so it's v1 plus v2. So from these two equations, I should be able to get v2. That's the one I wanted. So what we'll do is we'll cancel the m's here. And what did I do? I think I just added these two equations together. If I add these two equations, these two terms cancel, and you get 2v equals 3v2, or v2 equals, just bring down the 3, 2/3 v right there. So there's the speed that this one's going that way. Then I said the speed of the 2m after, and then this one's going to run into the 4m. Since he's running into something bigger, he's going to bounce back. Now, this guy's out of the picture, so now we just have this collision right here. The momentum before is 2m v2. Afterwards, we have 4m v4 minus 2m v3. So there's our momentum equation, and our relative speed is v2 is coming in, and since they're going in opposite directions, it's v3 plus v4. Now I wanted to get rid of the v4, so I figured the easiest way is I'm going to multiply this equation by 4, everything, and then just subtract these equations. Why? Because if I take the 4v4 and I subtract off this 4v4, I got no v4s, and so that's what I want to do. So we'll take the bottom one and we'll subtract off the top one. So you got 4v2 minus 2v2 is 2v2. 4v3 minus a minus 2v3 is 6v3, since we're subtracting a negative, and these two dropped out. So v3, which is what we wanted, was 1/3 v2, but v2 was 2/3, so that's 2/9 v right here. So the speed of this guy will be coming back at 2/9 speed. And then I also said, after all the collisions are done, what's the total momentum of all the three particles? Well, it's the same as the total momentum before everything started. What was the beginning momentum? It was just mv. So the total momentum at the end is the same as the total momentum at the beginning, which is just mv. Okay. The next one was someone running in on a merry-go-round right here. I think I even just did that one of these in the problems right here. And we ask, this is a mass m, and this is a mass m right here, and he's just running in. Initially, everything's rotating at omega naught. And now he runs radially to the center. Well, we're using angular momentum here, so I naught omega naught equals I final omega final. You're going in a circle. I have the person is mr squared. I have the disk 1/2 mr squared, omega naught. Then when he runs into the middle, he has no I. It's just I of the disk, 1/2 mr squared. Okay, so this is 3/2, and this is 1/2. All the mr squares drop out, and you get the final omega is 3 omega naught. Okay, so there is your final. Then I said, what is the frictional force when he's standing out on the edge? Well, when he's standing out on the edge, the only force he has inward is the friction, and that's equal to mv squared over r. We can turn our v's into r omegas. Now this is the original, not the final. This is because where he's at the beginning right there. And square that and cancel one of the r's. So there is the original frictional force right there. And then what's the work due to the person to walk in? Work, he's the only one doing any work, so whatever he does is the total work, which is the change in kinetic, which is the final kinetic minus the initial kinetic. The final kinetic is just the disk. Final omega squared is 9 omega naught squared minus the initial 1/2 I. Originally, it's both of them put together. It's 3/2 mr squared omega naught squared. Okay, and then we can just combine these two together right here. This is 9 force, this is 3 force. 9 force minus 3 force, which is 6 force, which is 3/2 mr squared omega naught squared. Okay, and then the last one was, here I gave you some points, 4m at point minus 3, 0. m at 1, 3, and 2m at 3, 2. And I said, what is the y position of the center of mass? It's just, it's 2m times the y value, so that's 4m. This one is m times 3, which is 3m, and this one is 0, so it's 3m plus 4m plus 0 over 7m. The m's drop out and you get 1. So the y center of mass is right at the y equal 1. And then I said, what if we rotated about the x-axis? Now you're rotating it around the x, which means we're going around this way. So the radiuses are their y values, because this is the way we're spinning it right here. So this one would be 2m times 2 squared, which is 4. This would be m times 3 squared, which is 9. And this would be 4m times 0 squared, which is 0. So this is just 8 and 9, 17m. And then the last one is determine the moment of inertia about a line parallel to the y-axis, but passing through the center of mass. So we're really looking at a line going right through y equal 1 right here. We could have just figured out what the radiuses were, but I figured I'll use the parallel axes theorem. We do know that the I about the y is equal to I about the center of mass plus md squared right here. So, actually that should be x right there because we're rotating about the x right here, x-axis. So I about the center mass is I about the x, which is 17 minus the mass, which is 7m times the distance from the x-axis between these two axes, which is 1. So it's just 17m minus 7m, which is just 10m. Remember, we're finding it about this axis right here. If you wanted to, you could have just said it's this mass, but his radius is just 1 now, plus this mass, his radius is just 2 now, plus this mass times his radius is just 1 now. And you could have done that and you would have come out with the 10m right there. Okay, so hopefully this test wasn't too bad right here.